in these states of matter, first is what type of attractive forces present in different states. States of matter means it is divided into solids, liquids, and gases. First, we start with what type of intermolecular force are present in between this gaseous and liquid state. What are the intermolecular forces, which also called as a van der Waals forces. So these van der Waals forces are divided into, first one is called as a London forces, or we can call it as a dispersion forces. Second is called as a dipole forces, and the next one is called as the dipole induced dipole forces. Dipole induced dipole forces. Next one is called as the ion forces, and the next one is called as the ion dipole forces. Ion dipole forces. These are different types of van der Waals forces present in between gaseous molecules. First, we start with the London forces. One more name is also called as the dispersion forces. Dispersion forces. It is applicable for what type of molecule? Non-polar molecule. In non-polar molecule, what is very for very short time or instant time, this charges electrons are moved to one side. So because of this dispersion of charges in between positive nucleus and electrons, some attractive forces are possible. These are called as the London force or dispersion forces. It is operated at the distance of 1 by r to the power of 6. And London force or dispersion forces depends on size of molecule. When size of molecule increases, this type of forces always increases. And when surface area or size, surface area increases, London force also increases. So whenever surface area, size of molecular weight increases, London force or dispersion force also increases. And the second type of important forces are dipole forces. So this type of forces operating in between molecules which are polar in nature. We take an example. Example is HCl molecule, and we take one more HCl molecule. In HCl, chlorine charge is minus, hydrogen is plus. In this HCl, chlorine is minus and the hydrogen is plus. In between this partial positive chlorine and partial negative hydrogen, these are called dipole also. Two poles are present, two charges are present in between negative chlorine and positive hydrogen. The attractive forces are called dipole forces, and it's operated at the distance of 1 by r to the power of 6 when molecules are rotated, and 1 by r to the power of 3 when molecules are stationary. So these are called dipole forces, and next type of van der Waals force are called as the dipole induced dipole forces. Dipole induced dipole forces. So we take an example HCl, and one more example H2 or Cl2 molecule. We take HCl and Cl2 molecule. So here HCl, chlorine is partial negative, hydrogen is partial positive. In chlorine molecule, because of positive hydrogen, here this chlorine negative charges increases, and a temporary dipole is induced by this dipole molecule. In between, attractive forces are possible. It is called as a dipole induced dipole forces. Again, it is operating at the distance of 1 by r to the power of 6. And next is the ion forces. What is that? Ion forces. So we take an example, sodium and chlorine in ionic compound. These attractive forces are called electrostatic forces, which are very strong in nature, and sodium chloride is formed. This is called as a ion forces. These are different types of intermolecular forces operating in between molecules. First, we start with the gaseous state. So, what are the measurable properties of gases? So, here, gases, some properties are there: pressure, volume, temperature, number of moles. These four properties are called as a measurable properties of gases. So, first, we start with the pressure of the gas. Pressure means here pressure of a gas is present in atmosphere. So pressure of gases present in atmosphere can be calculated by a barometer. What is this barometer? It contains a inverted funnel with contains mercury. Here atmospheric pressure. This is the vacuum created in that inverted tube. Inverted tube. From that we can find out the pressure. So pressure is equal to height of the mercury column, density of mercury, and also depends on gravitational forces. So, what is the pressure of atmosphere? We can take it as 1 atmosphere is equal to that is the unit 760 millimeters of mercury. That is equal to 76 centimeters of mercury or 14.2 psi. That is the pounds per square inch. That are the pressure or 760 torr that is equal to what is that 1.01325 what 1.01325 into 10 to the power of 5 pascals. These are the important units of pressure in present in that atmospheric pressure. So what is the pressure of the mixture of gases can be calculated by barometer, but pressure of individual gas, how to calculate pressure of individual gas? That is the pressure of individual gas or separate gas from that mixture. Individual gas can be calculated by using of manometer. Here, manometer is two types. That is called as the open-end manometer, and next is called as a closed-end manometer. So this manometer contains two limbs, and here this is connected to external gaseous pressure. So in these limbs, mercury is present. So mercury is present in this two limbs. One is the shorter limb, one is the longer limb. In case of this is a closed-end manometer, here pressure of gas, individual gas is equal to H. We can take H means height of that mercury column, or H is equal to difference in height of that mercury column. So this is called as a closed-end manometer. In case of open-end manometer, this is the open-end manometer. Here one side it is influenced by atmospheric pressure. In open-end manometer, this is open-end manometer, pressure of the gas. Here two limbs, one is the shorter limb, one is the longer limb. Here two limbs are present here. One is shorter and one is the longer limb. So pressure of gas is equal to atmospheric pressure plus what is the height of that mercury column, plus height of mercury column. If it is different in state, what is this? Here, this is the two limbs are present in this. Two limbs are present here. This is the difference in this mercury levels. This is the difference in mercury levels. So here in this case, if the longer limb mercury level is less, then pressure of gas is equal to atmospheric pressure minus H. We can take H is equal to difference in mercury column. So pressure of gas, individual gas can be calculated by manometer, and a mixture of gases present in atmosphere calculated by barometer. And the next one is volume of gases. Volume is 1 decimeter, 1 cubic meter. So units here, 1 cubic meter is equal to 10 to the power of 3 decimeter cube, or it is equal to 10 to the power of 3 liters. So 1 decimeter cube is equal to 1 liter, 10 to the power of 3 liters, that is equal to 10 to the power of 6 milliliters, that is equal to 10 to the power of 6 cubic centimeters or centimeter cube. So this is the units of volume of gases. And next, gases occupies entire available space. Next is called as a temperature. So important units are two. First is the temperature, normal degrees Celsius. We can take 0 degrees Celsius. If you take thermometer, it is divided into 0 to 100 degrees Celsius. And one more also there, that is called as a absolute scale temperature, Kelvin scale temperature, absolute or Kelvin scale temperature. So according to this Kelvin scale temperature, temperature is equal to what is that, degrees Celsius plus 273.15 Kelvin. So here we use this any one of this scale, temperature scale and the Celsius scale and also Kelvin scale. So this is a what is the temperature units, and number of moles is equal to weight of gas weight by molecular weight of gas. So number of moles always equals to weight by molecular weight of gas. In CGS system, weight is we can take in grams. In a SI system, we take weight in kilograms. So these are the measurable properties of gas molecules. Now we'll discuss about this gas loss. Gas loss, what is that? This all gas loss will get a relation between any two of measurable properties, and remaining measurable properties becomes constant. We get a relation between any two measurable properties and remaining properties becomes constant. It is called as the gas loss. First gas law is the Boyle's law. For Boyle's law, what is the temperature is constant for given amount of gas, and we get a relation between pressure and volume. According to Boyle's law, pressure inversely proportional to volume, or we can take it as a P is equal to constant by V. Okay, or we can take it as log P plus log V is equal to, we can take it as constant, or P1 V1 is equal to P2 V2. We use this also. Or density is equal to mass by volume inversely proportional to volume. So we can take a P1 by T1 is equal to P2 by D2. Also we use this formula. So this is called as a Boyle's law. Here pressure is constant in this, temperature is constant for given amount of gas. Given amount, this means mass also constant, given amount of gas. First gas law, which gives the relation here. This is the relation between pressure and volume. And the graphs are called isotherms also in case of Boyle's law. What is the uh, graph? We get pressure, and if you take 1 by V, pressure is equal to 1 by V, direct relation. And here We get this graphs at different temperature conditions, T3, T2, T1, T3 greater than, T2 greater than T1 here. These are called isotherms also. These are called isotherms. Or we get this relation also. Pressure and B, we get a rectangular hyperbola. This is called as the isotherm. It indicates pressure inversely proportional to volume. Or we take one more graph here, log P plus log 1 by B. So from this, what is the relation we get? We get this relation, and this is called as a log K. Intercept is a log K. Or we get one more graph here, that is PV is equal to constant. PV by V, we get a constant. Or PV with P also we get a constant. Or we take one more graph here, log P, log V, we get this relation. First gas law, Boyle's law, and next gas law is called as a Charles law. So what is this Charles law? He observed that volume of gas directly proportional to temperature. In this method, we use a one gaseous tube which contains a 273 ml of gas. With increase in temperature 1 degree Celsius, what is the gas volume also increases to 274 ml, and 2 degrees Celsius we get gas volume increases to 275 ml. From this, he observed that volume of gas increases or decreases by 1 by 273 times with increase in temperature by 1 unit. So volume directly proportional to temperature, or we can take it as a volume at T temperature is equal to initial volume plus 1 by T by 273. This is also we get the relation between this volume and temperature, or we can take it as Vt is equal to V naught into 273 plus T by 273. So here Vt is equal to V naught into, we can take it as capital T by small t. Capital T is called absolute zero temperature, or we can take it as Vt by capital T is equal to V naught by small t also we can take. So this is the relation between volume and temperature. So this graph, what it indicates here, this indicates that when we take the graph between temperature, volume of the gas, this is volume of gas. If you take a pressure of the gas at a minus 273 degrees Celsius is a final temperature where that no gas is exist. So at a minus 273 degrees Celsius is nothing but 0 Kelvin. This is absolute 0 Kelvin temperature. At this temperature is the minimum temperature that gases or solids or liquids or exist. So this is called as a Charles law, and volume and temperature relation we get here. This is called isochore. What is meaning of isochore? We get this relation at constant. What is that? Isobars. What is the isobar? We get a relation between these two at a constant pressure. So this is called as a Charles law. Next is the Avogadro's law. So what is that? Volume directly proportional to number of moles at given temperature, pressure is constant. For given temperature of temperature is constant, pressure is constant, volume of gas directly proportional to number of moles, or we can take it as V is equal to K, and this is called Avogadro's law. So from all gas laws, what is that? We get ideal gas equation. So what is ideal gas equation? PV is equal to N or T. This is called ideal gas equation, or we can use a P1 V1 by T1 is equal to P2 V2 by T2 also. Ideal gas means in between gas molecules, no attractive or repulsive force of present, that is called ideal gas. So from all gas laws, we get this ideal gas equation. PV is equal to nRT. R is called as R is equal to PV by NT. R is called universal gas constant. If pressure we can take at 1 atmosphere, volume is 22.4 liters, 1 mole and 273 Kelvin. Temperature we get 0.0821. This is liter atmosphere pressure per mole per Kelvin. Per mole per Kelvin we get relation, we get R value. So what are important R values which are used in exam, any competitive exam? One is called as a 0.0821 liter atmosphere per mole per Kelvin and 0.083 bar per liter mole per Kelvin, bar liters mole per Kelvin. This is also one unit, or one more unit is 8.314 joules per mole per Kelvin. We know 1 joule is equal to 10 to the power of 7 H. So we write here 8.314 into 10 to the power of 7 H per mole Kelvin. These are different units, or 2 calories, 1.987, or we can write 2 calories per mole per Kelvin. So these are different units of R value. This is called ideal gas equation. And next gas law is Dalton's law. Dalton's law of partial pressures. So this law mainly applicable to what type of gases? It is mainly applicable to gases which are in between the gas molecules and there is no attractive or repulsive force are present. We take one example here. This is one vessel. We take a volume is equal to, we take it as 1 liter, one container. Here N2 gas is present and one more container. We take example O2 gas is present with volume is 1 liter. N2O2 is not involved in reaction at normal conditions. At a very high temperature conditions only, nitrogen involved in reaction with oxygen, and we maintain same conditions of pressure, same conditions of temperature. So same conditions of temperature we maintain, and volume also same. And if these two gases placed in same container with 1 liter volume only, so pressure of N2 is a PN2, pressure of O2 is equal to PO2, and this is the total pressure in a volume 1 liter. Total pressure is PT, and this total pressure of gases is equal to pressure of N2 plus pressure of O2. These are called partial pressure of gases also. When we apply that ideal gas equation, what is the value we get? Pressure of mixture of gases is equal to PV is equal to nRT. We know that N1 a number of moles of N2 plus number of moles of O2 into RT by total volume. If temperature conditions are constant, we maintain. From this relation, we get partial pressure is equal to partial pressure of N2, which we take. Partial pressure of N2 is equal to mole fraction of N2 into total pressure of the mixture. The same way, partial pressure of individual gas like oxygen is equal to mole fraction of oxygen into total pressure of the gas. So Dalton's law, it is applicable to what type of gases? Non-reacting gases only. We can take example NO. It is not applicable to reactive gases like N2O2 only. It is applicable. And what are the non-reacting gases? N2 and H2 it is applicable. And CO2, SO2 also it is applicable. And H2 and O2 which are not involved in reaction at normal conditions. Next is NO2 plus O2 also not involved in reaction at normal condition. For this type of gases, this Dalton's law of partial pressure is applicable. What is important, the use and application of this Dalton's law? Many gases in experiment collected over water So the gas contains some aqueous tension also, pressure of water vapor also. So total pressure is equal to aqueous tension plus pressure of the gas. What is the partial pressure of the gas? So partial pressure of gas is equal to total pressure minus aqueous tension. We can calculate this aqueous tension is constant for given gases at given temperature. So this is one important application of this Dalton's law of partial pressures. And next is the next gas law is Graham's law of diffusion or effusion. Next gas law is Graham's law of diffusion or effusion. What is this Graham's law of diffusion or effusion? So first that gases shows one property, intermixing. In between gases, space is more, so one gas can be moved to other side, and in between spaces, other gas are mixed. Intermixing is called as a diffusion. And when gas is present in a high pressure region and with a small hole, this is enter into low pressure region, that is called as a effusion. So, according to Graham's law, effusion or diffusion of gas is equal to directly proportional to the rate of effusion or diffusion of gas, directly proportional to volume and inversely proportional to time for effusion or diffusion. Here, R is equal to speed of effusion or diffusion. V is equal to volume of gas effused or diffused. T is equal to time for effusion or diffusion. And effusion or diffusion inversely proportional to molecular weight also. So R inversely proportional to molecular weight of gas or R inversely proportional to density of gas also. So we write here R is equal to, we can take K by root molecular weight of gas. R is equal to K by density of gas or vapor density of gas also. And R directly proportional to pressure. Again, pressure is more, rate of diffusion is more. So what are different formulas used in effusion or diffusion? So here R1 by R2 is equal to P. What is that? Root M molecular weight of second gas by molecular weight of first gas. Or R1 by R2 is equal to V1 by T1 into T2 by V2. R1 by R2 is equal to root D2 by D1, or density, or we can take vapor density also, or R1 by R2 directly proportional to pressure, P1 by P2 root molecular weight 2 by molecular weight of gas 1. This is a effusion or diffusion of gases. And what is important application of Gram's law of diffusion? So detection, it is used in marsh gas alarm. Marsh gas alarm in coal mines. What is marsh gas alarm? Explosives H4 is detected and it is used in ANSYS alarm. What is ANSYS alarm? Here, this alarm is the detect that the poisonous gas evolved, which is again used in coal mines. And the uranium isotopes are separated by this method. Uranium 235, uranium 237, these isotopes are separated by diffusion only. And one more important application is atmolysis. Atmolysis also based on diffusion. Atmolysis means mixture of gases. The mixture of gases, the individual gases are separated by atmolysis method. So this is called as a Gram's law of diffusion. After that, next is kinetic gas equation. So kinetic gas equation applicable to again ideal gas only, proposed by Maxwell and Boltzmann. What is this important postulates of kinetic theory of gases? It explains about microscopic properties of gases. Microscopic model also it is called. According to this kinetic gas equation, gaseous molecules are not attracted by gravitational forces. So there is no gravitational forces on gas molecules. and gas molecules randomly moves in all directions in straight lines, and gas molecule collide with each other. In these collisions, energy is transferred, but the total energy is always constant, and kinetic energy directly proportional to temperature of gas. So this is a kinetic gas equation, and according to this Maxwell's Boltzmann kinetic gas equation, PV is equal to 1 by 3 mnc square. This is the weight of the gas. N is equal to number of moles of the gas. M is the weight and N is number of moles. C is called as a RMS velocity of the gas, or it is called as a root mean square velocity of gases also. Okay, what is the kinetic energy of gas molecule? So kinetic energy of gas molecule is equal to, we can take a 3 by 2 NRT. We use this formula for n moles of molecules. So for 1 mole of molecule, kinetic energy is equal to 3 by 2 RT. We can take. Okay, and here K, what is the, you can write for 1 molecule also. We can take, this is for 1 mole of gas. This is for n moles of gas. We use this for 1 gaseous molecule. What is kinetic energy? Kinetic energy is equal to 3 by 2 kT. We can take. What is K here? K is equal to R by N. K is called as a, what is that? It is called Boltzmann's constant. K is called Boltzmann's constant. We can call it as Boltzmann's constant. And what is the K value? K is equal to 1.38 into 10 to the power of minus 23 joules per Kelvin per molecule. That is a, what is that Boltzmann constant value? And next, when you compare two gases, kinetic energy of first gas by kinetic energy of second gas, we use this formula N1 by N2, number of moles of gases into what is the temperature also, because kinetic energy directly proportional to temperature of the gas. So this is the kinetic energy of gas molecules. Next is what is that molecular velocities of gases. Here again, molecular velocity directly proportional to temperature. Molecular velocity, when temperature increases, velocity of gas molecules increases. Molecular velocity of gases here. When we take the fraction of molecules compared to total number of molecules and the velocity of gases, we get this graph. So first here is, what is that most probable velocity. Second is called as a average velocity. Third is called as a, what is the third one is called as a RMS velocity. So three types of velocities are there. So when you take fraction of molecules, if you take fraction of molecules when you compare with the total number, most probable velocity fraction is more. Maximum gases shows this velocity by average, and it is greater than RMS, which is called as a root mean square velocity. What is this most probable velocity? Root 2 RT by M. PV is equal to RT for 1 mole of gas. So we can take it as root 2 PV by M also. And density is equal to mass by volume. So we can take as a 2P by D also. Root 3 2P by D. This is called as a most probable velocity of gas. And average, we take average of velocity of all gas molecules. So right here, root 8 RT by pi M, or this is equal to, instead of RT, we can write P, root 8 PV by pi M, and V by M, density here inversely proportional to, you can write root 8 P by pi D also we can take. So this is the average velocity. Next is root mean square velocity, root of mean of velocity of all gas molecules, and this is equal to root 3RT by m, that is equal to root 3PV by m, that is equal to root 3P by D. Okay, these are different velocities of gas molecules. So your velocity, any type of velocity, inversely proportional to molecular weight and directly proportional to temperature. So means at same temperature, if you compare two velocities, C1 by C2, when you take care same temperature, so we write this formula, molecular weights. And if we use a different temperatures, C1 by C2, when you compare two gases velocities, that is equal to root T1 by T2 into molecular weight 2 by molecular weight 1. And next is average velocity. When you compare relation between different velocities, average velocity is equal to 0.9213 into RMS velocity. The relation between different velocities, and most probable velocity is equal to 0.8166 into RMS velocity. These are relation between different types of velocities of gas molecules. To take most probable and average and RMS velocity, to take ratio. What is the ratio? Is 1 is to 1.2 is to 1.12 is to 1.22 we get. This is the relation between most probable, average, and also RMS velocity of gas molecules. And next concept is compressibility factor. What is that? It explains about relation between ideal gases and also non-ideal gases. So what is this ideal gases? In ideal gases, in between gas molecules, attractive and repulsive force are not present. In non-ideal gases, in between gas molecules, attractive or repulsive forces are present. That is called non-ideal. So ideal, no ideal gases exist, but few gases show some ideal nature. So this relation between ideal and non-ideal gases can be that is explained by compressibility factor. What is this compressibility factor? Compressibility factor is indicated by Z. Compressibility factor is equal to volume of real gas by volume of ideal gas. This is called as the compressibility factor. And we know that according to ideal gas equation, PV, this is ideal, this is equal to NOT, or V is equal to, for ideal gas, NOT by P also we get. Z is equal to volume of real by NOT into P. We get this relation. Z is equal to PV by NOT. And if you take ideal gas, Z is equal to 1 for a perfect gas or ideal gas. In case of this is applicable for ideal gas, and Z is not equal to 1 for what type of gas? Non-ideal. That is called as a real gas. Z is not equal to P. Z is not equal to 1. Again, there are two types of gas are there. Some gases show the negative deviation. Some gases show positive deviation. We draw one graph here, Z, that is equal to PV by RT, NRT for n mole of gases. Here pressure we can take it is in bar or atmosphere, and we get this graph for ideal gas and real gases. Initially, what is that? This is Z is less than 1 and this is Z is greater than 1. Few gases they show Z is greater than 1, like hydrogen gas and helium gas. They show Z is greater than 1. For gases like what is that? CO2 or gases like CH4, they show negative deviation. So initially, when pressure increases, they are what is that? They are closely arranged, but at high pressure, again, repulsions are more. slowly they show some ideal nature. This is the ideal nature here. And high pressure, again, it shows a positive deviation. Very high pressure, gas are very closely arranged there. Instead of attractive forces, repulsive forces operating. So they show Z is greater than 1. And these gases cannot be converted into liquid state. In between these gases, attractive forces are not present. What is that? Hydrogen and helium, which the gases shows a negative deviation that is less than 1. They are converted into liquid state. We can convert into liquid state. This is called as a compressibility factor of gases. So Van der Waals equation is corrected here. So what is this Van der Waals equation? For ideal gas is corrected by Van der Waals equation. What is this Van der Waals equation for real gases? In between real gases, attractive and repulsive force are present. And real gases cannot move in all directions. Some space is not available for free movement of gas molecules. That is called as a restricted volume. So here, according to Van der Waals equation, P plus A square by V square into V minus NB is equal to N naught T. This is called as a Van der Waals equation. What is this? B indicates it is called as a restricted volume. Means some volume is not available for free movement of gas molecule. This is a gas molecule. Some space is not available for free movement of gas molecules. We can take it as what is that? This volume. This is here 2R. And this volume, what is this? This volume. This volume. This volume is called as a what type of volume? It is called excluded volume, which is not available for free movement of gas molecules. So this excluded volume is indicated by B, and B is equal to it is equal to 4 times the volume of ideal gas. So B is equal to excluded volume, and in between real gases, attractive or repulsive force are present, and that attractive or repulsive force is indicated by one constant that is equal to A. So here A indicates the attractive or repulsive forces, and B indicates that volume is not included. A is attractive, B is repulsive forces. Where any gas contains higher A value, okay, so A and B are independent on temperature, higher A value, that gas can be easily converted into liquid state. If any gas contains a higher B value, that gas cannot be converted into liquid state. So, what is this? A is equal to what it indicates. This does not depend on temperature, and it depends on attractive forces only. And what are the units of A? Atmosphere, liter square per mole minus 1, mole minus 2. B is equal to excluded volume, which is not available. Excluded volume, that is liter per mole. This is called as the excluded volume. So this is called Van der Waals equation. Again, any gas contains higher A value can be converted into liquid. Any gas contains a higher B value that is not easily converted into liquid state, and B is equal to 4 times volume of a gas molecule. It is called as a excluded, or the volume which is not available for free movement of gas molecules. So when we apply in the calculation part, if you maintain low pressure conditions, so low pressure conditions in between gases, there is no repulsive forces operating. So we can neglect B value at low pressure conditions. So we write here P plus 1 mole of gas, P plus A by B square into B is equal to RT. For 1 mole of gas, we use this. Or when it is multiplied, we get a PV plus AB by B is equal to RT. Also, we can take, sorry, A by V, because this is cancelled. PV plus A by V is equal to RT, we can take. If PV and PV is equal to RT minus A by V, take. And when these two equations are divided by RT, divided with RT. What is the value we get? PV by RT is equal to 1 minus A by RT we can take. So PV by RT is called as a compressibility factor. Z is equal to, what is the value we get? 1 minus A by RTV. When it is possible at low pressure conditions. At low pressure conditions, excluded volume is neglected because there is no pressure operating. And next is the high pressure conditions. In high pressure conditions, we neglect attractive forces. A is neglected in this case, very high pressure condition, because in between very close gases, their repulsive forces are more, so A can be neglected. So we write the Van der Waals equation, P minus Vp is equal to RT for 1 mole of gas. Or we can take it as a PV by PV minus PB is equal to RT. Or PV is equal to RT plus PV. Or this total equation is divided with RT. Divided with RT, we get PV by RT. We get this. Or this is nothing but a compressibility factor. Z is equal to 1 by PB plus RT value we get. This is at low pressure, at high pressure conditions. So very low temperature and very low pressure and very high temperature conditions. A, B both are neglected and we get the ideal gas equation. PV is equal to NRT. So it indicates that at what is that? At low temperature and high pressure, real gases behaves like ideal gases. And the next important concept is Boyle's temperature. What is this Boyle's temperature? So Boyle's temperature indicates that at some temperature range and pressure range, pressure range, some range of pressure, real gas behaves like ideal. Okay, at this temperature, at what temperature and in that pressure range, real gas behave like a ideal nature, that is called as a Boyle's temperature. Boyle's temperature is indicated by TB. TB is equal to A by B or we get Boyle's temperature. Real gases, they show Z is greater than 1. What it indicates means above this Boyle's temperature, real gases shows Z is greater than 1, above Boyle's temperature. This is above Boyle's temperature. Z is less than 1. What it indicates? Below Boyle's temperature, real gases shows Z is less than 1. And next concept is how to convert into gases can be converted into liquids. So this is called liquefaction of gases. Okay, there are two methods we use. One is called as a Joule-Thomson's method. Here, in this method, one gas is passed through a spiral tube which contains very small nozzle. When gases move through this spiral tube through this nozzle, they move from high pressure to low pressure side. So sudden expansion of gases takes place. Because of sudden expansion of gases in between gas molecules, what is that? Kinetic energy decreases. So when kinetic energy decreases, gases are very closely arranged. When gases are very closely arranged, in between gases, attractive forces are operating and gases converted into liquid state. This is called as a liquefaction of gases and it is called Joule-Thomson's method. So when it is applicable to carbon dioxide, So carbon dioxide, when it is applicable, here pressure and it is volume. We get isotherms. We get isotherms here. We get isotherms. And at particular temperature, particular pressure, at particular volume, that CO2 gas is converted into liquid state. So every gas contains a temperature, pressure, and volume that is converted into liquid state. That pressure is called, that is indicated by PC, critical pressure, at which gas is initially they are converted into liquid state at particular temperature and pressure. That is called critical volume. And what temperature we use to convert gas into liquid state, that is called as a critical temperature. So critical pressure PC, at which pressure gas is converted into liquid state, critical volume at what conditions, at what volume gas is slowly converted into liquid state, and the temperature PC indicates at what temperature gas is converted into liquid state. And in case of gases, what is that? Ideal gases, what is this VC value? VC value always equal to 3V. V is equal to again repulsive forces. And what is this PC value? A by 27 B square, that is equal to PC value. And what is PC value? 8K by 27 RB. R is a gas constant. B is equal to Van der Waals constant. So this is called as a critical temperature, critical pressure, and critical volume. And next is the liquid state. What is that liquid state? Liquid shows some properties that is called vapor pressure. First property. What is meaning of vapor pressure? If you take a liquid, one liquid we take, this is the surface molecules, these are the bulk molecules. Bulk molecule equally attracted by all sides by other molecules. What is that? Which molecules? Bulk molecule. But the surface molecule is attracted by one side only. Means in case of surface molecules, energy is more. When temperature is given, the surface molecule is converted into vapor state. If it is placed in closed container, again the vapors are condensed back. Vapors are condensed back when we placed in closed container. So at evaporation takes place and also condensation takes place. So at particular temperature, rate of evaporation is equal to rate of condensation. This temperature is called as a this at this condition the pressure is called as a vapor pressure. If vapor pressure equal to atmospheric pressure, that is called as a boiling point. Rate of evaporation again depends on surface area of that liquid. If surface area increases, what is that? Evaporation increases, temperature increases, evaporation increases, and in humidity increases, evaporation always decreases. Okay, this is a vapor pressure. We take next concept is surface tension. Here we take example, one liquid molecule. This is the liquid state. In between this is a surface molecule. We know that adjacent molecules, some attractive forces are present in between adjacent molecules. This is a surface molecule. In between adjacent molecules, some attractive forces are present. And bottom side also the molecules, some attractive forces are present. So here, forces acting along surface of liquid at right angles to any line of unit wavelength. This is called as a surface tension. So this molecules attracts the molecule, surface molecule to bottom side. So because of this, these molecules to overcome these forces, they attract to each other very strongly. Because of this, surface area of molecule decreases. That is called as a surface tension. And what is energy required here because of surface tension? Surface area decreases. And what is meaning of surface energy? Surface energy, energy required to increase the surface tension, that is called as a surface energy. Units are per meter square. So surface tension, what is that? When temperature increases, surface tension of that molecule decreases. So we take some examples of surface tension. Capillary action of what is that? Liquid molecules in plants. Capillary action of a molecule. What is that capillary tube molecule move to this side? That is based on surface tension only. In plants also, water is absorbed by the concept of surface tension only. And any drops, water molecules are spherical in nature because of surface tension only. One more property of liquid is viscosity. What is meaning of this viscosity? Resist to flow. Any liquid shows a more resistance to flow. That is called as a viscosity. And viscosity is indicated by what is that force of viscosity here. F is called force required to maintain the viscosity is equal to, this is eta. What is this? Eta indicates proportionality constant or proportionality coefficient of viscosity, and this depends on area of the liquid, and depends on dv by dx. This is called as a what is that? Velocity gradient. Means we consider the different layers of liquid. One layer of liquid shows repulsions on other layer, friction on other layer. So what is that? When the layer is, if you take a water tube, here it is a water pipe. This in between this water and this force, attractive forces are different. So adhesive force are present here. Because of this force, this layer is more attracted, it becomes stationary. And this layer, what is that? It shows some uh, friction on this other layer, and it shows some friction on other layer. So the friction is depends on area, and what is that? The friction is less. What is that? Velocity is more, and the force of this indicated by eta into a, the surface area, velocity, and x indicates the distance between layers. Okay, when distance between layers increases, force always uh, when distance increases, force of this viscosity always decreases, and this is the liquid state in this what is that? States of matter constant concept. And problems mainly based on Ground's law of diffusion and ideal gas equation, and also Dalton's law of partial pressures, and few problems on kinetic energy also. So we'll discuss one problem on what is that? Ground's law of velocity also. Few questions are there. Simple questions in the direct questions are based on formula only. You take example, you try to solve this example, calculate, this is one previous question, calculate RMS and most probable velocity of SO2, sulfur dioxide gas, at 27 degrees Celsius. All questions are based on direct formula only. And temperature first, any in this gaseous state are except thermodynamics. Remaining concepts, first you convert temperature into Kelvin scale. So what is that? We get 300 Kelvin. That is important. You convert first temperature into Kelvin scale. And what is the mass of the gas? That is equal to sulfur dioxide 32 plus 32. That is equal to, so answer is 16 plus 16. We get 64. Now we find out RMS velocity by the direct formula root 3RT by m. Whenever R units are not given, then you can use calories. That is simple method. Or generally we use joules in maximum cases, 8.314 joules, and temperature is 300 Kelvin by mass of gas is 64. So from this, what is the value we get? 3.42. meters per second. Whenever we use in joules, what is the distance is indicated by meters, and from this now we can find out most probable velocity. We use the direct formula 0.8166 into RMS velocity. From this we get a most probable velocity, that is 315. Uh, what is that? We get some 279 meters per second. In the same way, we can find out average velocity also. Average velocity, we know that 0.9213 into what is that? One more here, one more relation. Average velocity is equal to most probable velocity into 0.9213. So we use this relation and we can solve questions related to this type, and we'll discuss in remaining concepts in next class.